Hello and a very good evening to you from the Open University. We've one programme for you this evening. It's from the course Materials, Engineering and Science.
Electric light is so much a part of our daily lives, it's something we all take for granted. At the present time, there are many different varieties of lamp on the market, and all because of the developments that have taken place in materials and processing methods. The first electric light, the arc lamp. In this, two carbon rods with a voltage across them are brought sufficiently close that the air ionises. Electricity flows between them, generating both heat and light. In fact, so much heat that the carbon rods are slowly burnt away. Early experiments with electric lamps also met the need for light in another way, the incandescent filament bulb. These first lamps used a carbon filament which was heated until it emitted visible radiation.
Every household has several of them, incandescent lamps. You'll find them in the lights, in your motor car, spotlight, the slide projector, the torch, or the children's toys or the instrument panel. The basic idea is really very simple. A length of wire has a voltage applied to it, and the cross-section and electrical resistance of the wire are so chosen that it glows incandescent, without melting, and without evaporating, volatilizing or oxidizing. And because of that, it usually has to be placed inside an envelope to protect it. The higher the temperature, the better the light output, but the shorter the life. Now, although a lamp like this, it's called the GLS lamp, General Lighting Service, costs only a few tens of pence. There are over 70 different manufacturing processes go into the production. To say nothing of 20 different materials, each bringing with it its own property profile. Now we're going to look at just one of those, the light emitter, the tungsten filament. As you've seen, the early electric lamps used carbon filaments operating in a vacuum envelope. Compared with present-day lamps, their light output was poor, measured in candle power. Carbon filaments, however, were soon superseded by the more efficient tungsten filaments. All these early lamps had single straight-stranded filaments, whereas nowadays they usually have coiled coils. Why did such a design come to be evolved? We've had this lamp specially made up for us, with the filament in three different physical arrangements. Over here, it's a coiled coil. On this side, it's a single coil. And then the last part of it has been stretched out to become a single strand. But it's all the same diameter and it's all the same length of filament. Just watch what happens when I increase the current. Now already at quite a low voltage, you can see that the coiled coil is glowing quite brightly. Now we take it up further, and now you can see that the single coil is beginning to emit light. But the single strand is still not even red hot. Now, why has this occurred? Well, GLS bulbs are usually filled with a protective gas to reduce the volatilization of the tungsten. But it has a snag. It has a cooling effect. The sheath of gas is smaller over the single coil than it is over the single strand, and it's smaller still over the coiled coil. The coolant gas is taking more heat away from the single strand, which is consequently unable to reach the same temperature and emit as much light as the coiled coil, even though the same current is flowing. To show you just how much coiling there is in a filament, just watch this. Finer than a human hair. A metre of tungsten wire, all inside a bulb like that. But remember, we said at the beginning that tungsten comes with a package of properties. And there's one thing I haven't told you about yet. In common with most other body-centre cubic metals, tungsten tends to be brittle at ordinary temperatures. But from the way that wire stretched out, you can see that the problem's obviously been cracked. So let's have a look and see how it's been done. The starting point is doped finely reduced tungsten powder like this. A weighed amount is first poured into a die. The process is little changed from that devised by Coolidge in 1909. The top tool is placed in position and the whole thing goes under press to be compacted into a bar, which is then sintered in hydrogen to bond the particles together. The bar goes through various rolling processes to reduce the cross-section, and still at a high temperature, it then goes into a rotary swage, which hammers it to a much smaller diameter. However, the metal is still very brittle at ordinary temperatures. Tungsten can only be drawn into a wire above the brittle range, and this requires carrying out the operation initially above 1200 degrees Celsius. With more drawing, the ductile to brittle transition temperature is gradually reduced, so lower temperatures can be used at the later stages. Eventually, a fine wire is produced, which is ductile at room temperature. These micrographs show the grain structure of filament wire, with grains elongated and distorted by the drawing. In this condition, the wire is sufficiently ductile to be coiled into a filament at room temperature. It's first wound round a mandrel to form a single coil. This coil, mandrel included, is then wound round another mandrel to produce a coiled coil. Both mandrels will be dissolved out later. The coiling process generates high residual stress, and if this is not removed, the uniformity of the individual turns of the filament would be lost, with disastrous effects on the lamp's performance. To eliminate the residual stress, the filament is annealed at 1700 degrees Celsius before removing the mandrels. After stress relieving, it still needs to remain springy while it's being fixed and adjusted on the lamp's internal assembly. When it's in service, the filament will run at a temperature of about 2800 degrees Celsius, and the tungsten will then recrystallize. The recrystallized structure of pure tungsten can be seen here. But this wouldn't be at all suitable for a long service life, because these grains would slide past one another by a process called grain boundary creep. The filament would sag between its supports and eventually burn out. Dopants can be added, however, to control the directionality of this recrystallization, and this type of grain structure results. Its long interlocking grains are much more resistant to grain boundary creep, giving a considerably longer service life.
The basic process for manufacturing this long interlinked grain tungsten were established a long time ago. But over the years, the process has been made much more consistent and the interlinking is better, so we have a more stable filament. This leads to benefits in manufacture. We only need to use perhaps 2 filament supports, where a few years ago we would use 3. So that's a small saving in material, and it allows our machines to run faster with those benefits.
We've seen how improvements in the structure of tungsten wire have led to changes in production of GLS lamps. But have any other developments taken place?
Perhaps the obvious change is in the material for the cap. We previously used to use brass, but a process was developed which allowed the manufacture of caps with aluminium shells with a saving because it's a cheaper material. Inside the lamp, there have been some changes that are not at all obvious. The wires that take the current to the ends of the filament now use less nickel and copper than they used to. Some of it is still there, but steel is used as a base material.
The question a lot of people ask is why, with all these kinds of improvements, the average life of a light bulb is still only 1,000 hours.
The life of a lamp is governed by the rate of evaporation of tungsten. We can make longer life lamps by lowering the filament temperature, and this reduces the light output. When you buy a light bulb, you want a light, and it's only part of the purchase needed to achieve this. You need to buy the electricity as well. And if you take into account the cost of electricity over the period of the life of the light bulb and the cost of buying it, the balance comes out round about 1,000 hours for a convenient replacement period. If we take it any shorter, then it will be a nuisance to replace light bulbs, although in the case of higher wattage light bulbs, you really ought to be running lower than 1,000 hours now.
The light output of lamps is measured in lumens, and the number of lumens per watt of electrical energy is known as lamp efficacy. The best a tungsten filament can produce in this type of lamp is about 14 lumens per watt, whereas as many as 200 can be achieved by some sodium discharge lamps. We're all familiar with these yellow lights on roads and as security lighting, but sodium lamps distort colour. This is the lamp that gives rise to the yellow-orange colour, the low-pressure sodium discharge. The outer part is just a vacuum envelope to improve the thermal efficiency. The important portion of it is the arc tube, which is inside. All discharge lamps work on the principle of 2 electron emitters at the ends of an arc tube. Inside the arc tube is a substance which is going to vaporise. In this case, sodium. The arc is struck, the sodium vaporises, and the characteristic colour comes from the spectral lines of the sodium ions. But there's a snag. Lamps like this require an electrical ballast, partly to establish the arc, to stop the current running away while the sodium is vaporising, and to keep the light stable when it's running. And the light doesn't come on instantly. It's going to take several minutes before this works up to full power. I don't know whether I'd like one of these in my lounge. But there's another snag. How do you think the sports fan would feel if he was watching a game and he couldn't identify the colours of his favourite team? Now, although this is the most efficient lamp, the colour can in fact be improved and made much whiter by using high-pressure sodium vapour. And we're going to use the vital component in this type of lamp as our second example to demonstrate materials selection.
High-pressure sodium light was known about in the late 50s. It only became viable as a product with the development of a material that could contain the arc. Here is a 1 kilowatt high-pressure sodium lamp. And across here, we've actually got the arc tube itself. When illuminated, the centre of the arc tube reaches about 1200 degrees Celsius. It needs to be very resistant to the highly corrosive vapours of the sodium and mercury amalgam and must have very tight gas seals at the end. It needs to be impact resistant, and above everything, it must be translucent. The answer lies in the use of a ceramic material, alumina, which, like tungsten, brings its own property profile and its processing difficulties. The advantages of alumina are that it's a very high melting point, about 2300 degrees Celsius. It's also highly resistant to corrosive vapours such as sodium and is an excellent electrical insulator. Sounds perfect, so what's the problem? Well, for one thing, for the tube to actually be translucent, we need to carefully control grain growth and porosity. Secondly, we saw after sintering the tungsten, it was possible to draw it down to a wire by actually heating it. Thus, we're making the tungsten ductile. But this won't work for the alumina arc tube, where once sintered to shape, it cannot be reworked. So some way has to be found to close up the ends of the tube and make seals around the electrical contacts. Let's consider these two problems in detail. When particles of alumina are sintered together, there are many voids left between them which cause porosity, as this micrograph shows. Light is scattered by these pores and grain boundaries, and very little light is actually transmitted. Alumina can be sintered into large crystals with no voids, and the tube becomes transparent but cracks easily. This is because large crystals have different responses to thermal expansion in different directions. The solution: a compromise between transparency and grain size to give a high-density, translucent alumina. As with tungsten, the directionality of crystal growth in the alumina is obtained by doping. The pores have now disappeared. Very pure alumina powder is mixed with dopants to produce the arc tubes, but this powder has poor flow properties that make uniform packing of the die difficult. The die consists of a cylinder which fits onto a bottom punch. A mandrel is then located in the centre to create the hollow tube shape. The sprayed dried powder is then fed from a hopper at the top of the press, and the required amount flows into the annular hole in the die. The top and bottom punches then contain the powder. And finally, the pressure is applied isostatically via the polyurethane collar. The problem has been overcome by producing this free-flowing powder with slightly larger grains, which gives a consistent quality, dense packed tube each time. This powder is produced by mixing doped alumina with binders and distilled water, and then this slurry is spray dried. The spray dried powder then flows freely into the dies on an isostatic press. A mandrel in the centre creates the tube shape. Heating the press tube to 1000 degrees Celsius removes the binders. A suitable material has now been achieved, but before it can be used in an arc tube, the ends of the tube must be sealed. This is where product design and processing are very closely linked. Alumina plugs are produced and inserted into the ends of the tube. During the sintering process, the boundary between the tube and the plug disappears as the grain structure becomes continuous. This sintering stage takes place in hydrogen at 1800 degrees Celsius. When the alumina enters the furnace, it's very porous because the binders have been removed by the preheating process. But when it leaves, some 7 hours later, it's fully dense and has an even grain distribution. On the left is a tube prior to treatment, and on the right, just after sintering. Voids have been eliminated with this considerable reduction in size. We now have a partially sealed, translucent alumina tube, but we're still left with the problem of providing a gas-tight seal around the electrodes. The final seal is supplied by a glass ceramic whose expansion is intermediate between that of the wire and the alumina, so it won't crack in service. This end is heat sealed first, and then the sodium and mercury amalgam is added through the other end, before the second electrode is added. This process is carried out in an atmosphere of inert gas to prevent oxidation. This end of the tube is also heat sealed. The arc tube goes on to be incorporated into the complete lamp. But these lamps cost about £6, so what advantages can they offer compared with the GLS lamp?
The high pressure sodium lamp is about 7 to 10 times more efficient than the general lighting service incandescent lamp that we're used to in our homes. And as such, it finds its way into applications which are very cost conscious from the point of view of producing light cheaply. Most domestic incandescent lamps have a life expectancy of 1,000 or perhaps 2,000 hours. Nowadays in the industry we talk about the life expectancy of high pressure discharge lamps like the high pressure sodium lamp in terms of a survival curve. 50% survival at 24,000 hours is a typical value for a high pressure sodium lamp. 24,000 hours, of course, is some 3 years or more of continuous operation, so we're talking about a very long-lived product here.
In this factory, high-pressure sodium vapour lamps are being used to replace some fluorescent ones. But is there a suitable, more efficient replacement for GLS lamps?
In the home, the best alternative is a fluorescent lamp. The large discharge lamps give too much light, and we're back to what Swan said when he first developed the carbon lamp, that he had succeeded in subdividing the light. So we want a relatively small package of light that can be used in lots of places. Tubular fluorescent lamps are not very acceptable in the home, except perhaps in the kitchen, but modern technology has allowed the manufacture of very compact lamps, some of which can be fitted with a bayonet cap and have in this part an electronic ballast. It has about the same light output as a 60-watt light bulb, but it is only rated at 11 watts.
So savings in electricity are likely to dictate the replacement of the incandescent filament lamp in many applications. Can we look forward to even more dramatic improvements in the future?
And the history of light sources has been one of continued improvement as a result of improved materials and processes, and I can see no reason why this will not continue. Through new materials and certainly through improved processes, we will be able to deliver to our customers benefits which will perhaps be reduced cost, improved efficiency, or other performance characteristics. And so materials, as in the past, will be a key element in the development of lamps of the future.
The tungsten filament and the alumina tube are just two examples of how the most desirable material brings with it a package of properties which has interactions with the processing route, the design of the article, and the functions that it has to fulfill. And this may mean cracking some very hard technological problems which need an understanding of the basic material structure and behaviour. And it hardly matters whether it's a beer can or a space satellite. We have to address exactly the same problems.